with me, Nathan, and Chris, we'll be presenting our fall 2022 hackathon project, the Elitzur Vaidman Minesweeper game. Now, we're faced with the problem. Imagine for a moment that for your summer internship, you've been tasked with clearing a minefield full of light-sensitive mines. Now, lucky for you, the last intern who was there had spotted all the mines. However, regrettably, he wasn't able to find out whether the mines are duds or not. Don't worry, he is safe. He just decided to quit because, who likes looking at mines? Now, it is your job to find out whether these mines are dangerous or not. So how do you go about checking them? Now, the classic method would be just to shoot a laser at it and see if it blows up or not. Now, this is not a very good method whatsoever because there are two issues with it. One, if you don't flash the beam at all, you get no information out of it. So you have to shoot the laser at it in order to interact with it. But the problem with flashing it is that it will interact with the mine, and if it's armed, it will blow up. Like, it's either you don't do anything or you do something and it blows up. Okay? Now, enter these two Israeli scientists, Vaidman and Elitzur, and they came up with this thought experiment and had a solution with it using quantum mechanics. It would be called the Elitzur Vaidman bomb tester. So, if there is no bomb, there's a simple setup here. First, we have a photon emitter over here that shoots out a single photon. Now it enters through this beam splitter, which is like a Hadamard gate, and then there's these two mirrors that direct that photon to another beam splitter, which takes it out of superposition, and it either lands on D or C. Okay? And here is a GIF demonstrating this. As you can see, it gets put to superposition, so it either goes up and along or along the bottom, and then whenever it goes back to the other beam splitter, the interference of the states will lead to it going back into either that one of the detectors. Okay. Now, if there is a bomb, it leads to another complication. When the bomb now serves as kind of like a measurement device in a way and takes the photon out of superposition. Now, there are two scenarios with the bomb. Either it explodes and it leads to it collapsing. However, when the photon collapses from superposition, it goes along the bottom. However, there is another scenario, as you just saw, where it interacts in superposition, it interacts with the bomb, but it doesn't blow up, and it lands along the top. Now, this would be in a normal state. However, it gets put back into superposition at the beam splitter, and then it goes either or. When measured by the detectors, it shows as either or. And with the statistics, without the bomb, it's 50-50 for the detectors. However, if there is a bomb and it explodes, that's a 0% whatsoever. Nothing is being read by either of these detectors. But if the bomb is a dud or not alive, the superposition will still exist, causing the split 50-50, either along the bottom or along the top. And at the detectors, it's about a 25% chance each of them of detecting it. Now, what does this mean statistically? So, this 25% chance. So, the 0 represents us being uninsured. So, that means that we didn't get a photon back and the bomb was not active, okay? And next would be, another bad scenario would be the bomb exploded and our photon collapsed and it was destroyed in the process, leading the detectors to not detect it at all. And there's another scenario where the bomb was a dud, it was there, however, the photon was able to make it there and be detected. But what we really want is that this 1-0. This 1-0 means that it was in fact armed, but it didn't explode. Does that make sense? Okay, so in circuit notation, this would basically, as I explained before, there's this Hadamard gate, then the bomb would be a CNOT, which, dependent on the condition that it gets put in through, will change and collapse the state of our qubit 0, which would be our photon qubit, and it gets put back into a Hadamard. Either it goes back, it collapses from not collapses, but it would be put away from superposition, or it gets put into superposition, dependent on what the CNOT does. And these are the measurements that go back into a classical bit in order to get your results. Now, we have the Zeno effect. So we see, as we noticed, there's a 25% chance of getting the desirable result that we want. That is a problem. We want to, have a higher chance of surviving and getting the information we need. So we'll use the particular effect called the Zeno effect. Now, how it works is basically we're changing the rate of prediction of finding the bomb by rotating the qubit along an angle that gets incremented by a determined amount. The thing about the Zeno effect is that if there is no bomb or no dud, this doesn't do anything because the rotation doesn't have any effect on the qubit. And these are some notes that will clarify a little bit more about what I mean. So it gets repeated by a certain amount of times, an angle rotated. And so this is what it would look like in the model. So we have a bunch of the beam splitters or Hadamard gates, and it would keep on. And if there's a bomb, there would be a little bit more of a bias for it to reflect, and so it would just keep on collapsing from superposition to reflecting away, and so it gets detected by this detector. And how biased it is dependent on epsilon, which for our game would be dependent on the player. Now, there is still a chance of it blowing up, even with this model. And in circuit form, as we can see, the rotational gate is represented by Rx, and as we can see, with this example, it was pi over 6. However, the theta can be anything because it's determined by pi over epsilon, and epsilon is how many operations you wish to perform. The higher that number, the less likely the bomb will blow up, and more likely we'll get our desirable result. And the zero ket is basically returning that qubit, the bomb qubit, back to a 0 state. Now we can compare the results. As we can see, initially we had 25% chance for all of the result scenarios. However, now with our new improved one, we can see that we can actually get all the way up to about 70% of getting our desirable result.